Today we're going to introduce the idea of regular expressions. This is a simple algebraic notation that describes exactly the regular languages. In practice, it's very common to have a regular expression-like notation to describe patterns, such as patterns in text, and to have behind the scenes a compiler from regular expressions into finite automata, in particular deterministic finite automata, because these are the things that actually can be executed. So after introducing the notion of a regular expression, we're going to show you that you can convert any regular expression into an automaton, and also any automaton into a regular expression. That's the proof that the languages accepted by regular expressions and the various kinds of finite automata that we've met are exactly the same. The algebra you are most familiar with is probably arithmetic, using operators plus and times and operating on numbers. The regular expression algebra operates on languages, and it has three specialized operators. Regular expressions, like algebraic expressions, are built up by applying these operators to operand. So, regular expressions then describe languages by an algebra, and they, as I said, describe exactly the regular languages. We'll use L of E as the notation for the language described by the regular expression E, and we will describe regular expressions and their languages recursively. Regular expressions use three operations: the union, concatenation, and the Kleene star. Okay. The union of languages is the usual thing, since languages are sets. And here's a very simple example. Here are two sets, their languages, each with with three strings and with two strings. 0, 1 happens to be in both, so it will be once in the union. 1, 1, 1 is there, 1, 0 is there, and 0, 0 is there. So that's the common notion of the union on sets or languages. Okay. Concatenation is also a fairly simple operation. We'll denote the concatenation of two languages, say L and M, by juxtaposition, that is, L, M with no punctuation in between them. The language LM contains every string that is W concatenated with X, such that W is in L and X is in M. So here's an example. We are, in effect, multiplying the two languages. That is, we'll take 0, 1 from the first language, and we can concatenate it with 0, 0. That gives us 0, 1, 0, 0. We could also take 0, 1 again, concatenate it with 0, 1, and that gives us that. Then 1, 1, 1 concatenated with the two strings here gives us these two strings in the result. And 1, 0 concatenated with 0, 0 and 0, 1 gives us the final two strings in the result. Okay. Kleene star is probably something that you're least familiar with. If L is a language, then L star, which is called the Kleene star or just the star operator, is the set of strings that you can form by concatenating 0 or more strings from L in any order. That is, you can take one string from L, you take no strings from L, that would give you the empty string. You take one string from L. You take two strings from L, there can be any two strings, they don't have to be the same. You can concatenate them. You can take three strings from L, concatenate them, and so on. Incidentally, Stephen Kleene was the fellow who invented regular expressions and showed that they describe the same languages that finite automata describe. Okay. If L is a language, then L star, the Kleene star, or just star operator, is the set of strings formed by concatenating 0 or more strings from L in any order. Thus, L star would consist of the set containing the empty string. The empty string is always in the star of any language. language, because that represents no choices of string from L. Then with union with L itself. And then we can take two strings from L, so we take L concatenated with L. We can take three strings, and so on. Any numbers from L. Anything you can form by concatenating any number of strings from L will be in the language L star. So here's an example. Language L just has two strings, 0 and 1, 0. The star of that language, well, we can take no choices, that would give us the empty string. We could take one or the other string, that will give us these two. We can take two choices from the language L. So if both choices are 0, we get 0, 0. If we take 0 for the first choice and 1, 0 for the second, we get this 0, 1, 0. Or we can take 1, 0 for the first choice and 0 for the second choice. That will give us 1, 0, 0. Or we can make both choices be 1, 0, and that gives us the string 1, 0, 1, 0. There are three parts to the basis in the regular expression definition. The first part is for single symbols. Okay. If A is a symbol, then A also denotes a regular expression. The language that this regular expression denotes is the language with one string. That string has length 1, and the one position of that string has A in it. Okay. By the way, in order to distinguish A as a symbol or string from A as a regular expression, we usually make the regular expression boldface, but a context should help you to distinguish strings, symbols, and regular expressions anyway. Okay. The second part of the basis is the symbol epsilon. Okay. This is a regular expression, and its language is the language that has one string. That string is the empty string. And the third part of the basis is the empty set symbol. This is a regular expression, and its language is the empty language. Okay. The inductive part of the definition also happens to have three parts. Okay. For the first part, we can connect any two regular expressions by a plus sign, and this plus sign represents set union. That is, the language of E1 plus E2 is the union of the languages that E1 and E2 denote. The second part involves the concatenation operator. We can write one regular expression next to another to denote the concatenation of their languages. That is, E1 followed by E2 denotes the concatenation of the languages that E1 and E2 denote. As we shall discuss in a minute, we sometimes need parentheses to group expressions properly. So in some circumstances, we need to put parentheses around E1 and or E2. So we might, for example, see something like that. Okay. The third part is the star operator. If we follow a regular expression E by a star, then the language we denote is the clean closure of the language that E denotes. Again, it is in some circumstances necessary to put parentheses around the E to make sure the operators inside the expression E group properly, like that. As with other algebras, we can and must use parentheses to force the intended order for operations. For regular expressions, the order is star, then concatenation, then plus. You can think of plus, the lowest precedence operator, as analogous to addition in arithmetic. Concatenation is analogous to multiplication, and star as analogous to exponentiation, although in the case of star, there is no power to which its argument is raised. In a sense, star means raised to all powers. Okay. For example, the regular expression 0, 1 represents the concatenation of the language consisting of one string, which is 0, and the language consisting of one string 1. The result is the language containing the one string 0, 1. In general, any string of symbols as a regular expression represents the language that contains only that one string. The language of expression 0, 1 plus 0, that's this, is the union of the language containing only the strings 0, 1 and the language containing only the string 0. The language of 0 concatenated with 1 plus 0, that's this expression, is the two strings 0, 1 and 0, 0. Notice that we need parentheses to force the plus to group first. Without them, since concatenation takes precedence over plus, we get the interpretation of the second example, that is, this one, and obviously you would get somewhat different languages. The language of 0 star is the star of the language containing only the string 0. This is all strings of zeros, including the empty string. Here's a little more complicated example. It denotes the language that we've been playing with when we talked about automata, that is, all strings of zeros and ones without two consecutive ones. To see why this works, in every such string, that is any string in the language, each one is either followed immediately by a 0 or it comes at the end of the string. Now, this part of the expression, 0 plus 1, 0 star, denotes all strings in which every one is followed by a 0. Okay. These strings are surely in the language that we want, but we also want those strings that are followed by a final 1. Thus, we concatenate the language of 0 plus 1, 0 star with the union of two languages. One is epsilon, and concatenating with epsilon just gives us the same strings, that is those that don't have a final 1. And we can also concatenate with the language containing the string 1. That gives us any string in which every 1 is followed by a 0, and then it also has a final 1. Okay. We're going to show that regular expressions define exactly the regular languages. We already have three equivalent representations for the regular languages: DFAs, NFAs, and epsilon NFAs. We need to show that for every regular expression there is some automaton that defines the same language, and for this job we may as well pick the most powerful of the three varieties of automaton, the epsilon NFA. For the other direction, we need to show that every regular language is defined by some regular expression. Here we may as well start with the most restrictive variety of automaton, the DFA. We'll begin with the process of how you convert a regular expression to an epsilon NFA. The proof is an induction on the number of operators, the operators of course being the plus, concatenation, and the star that appear in the regular expression. And we're always going to construct an automaton that has a special form, which I'll show you on the next slide. The special form of epsilon NFA we construct is suggested by this sketch. There can be any number of states in the middle, but only one start state, as is true for any automaton, and only one final state, which is a restriction. More importantly, as we build larger automata from smaller ones, we never allow an arc into the middle or into the final state. The only outside arcs must come into the start state. That is, we might add arcs like that, but you can't add an arc that goes to a state that's inside. Okay, likewise, you can't add an arc that goes to the final state. Similarly, we never have an arc from any of these states except the final state to someplace on the outside. So you can't install some arc leaving like that. And notice that we put quotes around the term final in final state, because although this state is final if this is the entire automaton that we construct, if it's a piece of a larger automaton, then the final state will no longer be final in the larger automaton. Okay. The induction is on the number of operators in the regular expression. And here are the basis cases, the expressions with 0 operators. Okay. A regular expression without operators has to be one of the basis cases from the definition of regular expressions. If the expression is a symbol A, then the epsilon NFA we need consists of only a start and a final state with an arc labeled A from start to final. Obviously, this automaton accepts the language of the regular expression A, that being only the one string A. If the expression is epsilon, then it is sort of the same, except the arc is labeled epsilon. And if the expression is the empty set symbol, then we just have the start and the final state and no way to get from one to the other. Okay. Now we begin the induction. There are three cases depending on whether the outermost operator is union, concatenation, or star. Here's the construction for union. Suppose our expression is E1 plus E2. Both E1 and E2 have fewer operators than the entire expression, so the inductive hypothesis applies to these sub-expressions. We may thus assume that there is an epsilon NFA of the desired form for E1, and likewise for E2. We form the epsilon NFA for E1 plus E2 by introducing a new start state and a new final state. The old final states are no longer final. There are epsilon transitions from the new start state to each of the two old start states, and there are epsilon transitions from the old states to the new final state. If there's a path from the new start state to the new final state, it must consist of epsilon transitions at the beginning and end with a path that is either wholly within E1 or wholly within E2. So, for example, the path might look like this. Go here, and then wiggle around, could go through the same state many times, finally comes to the old final state of E1, and then out to the new final state. Notice the fact that there's no way to get into the green thing labeled for E1 and no way to get out of it except, as I've shown, guarantees that the path must, from here to here, must either go through E1 or through E2. There are no other options. Okay. Here's the construction for concatenation of E1 and E2. Again, we assume by the inductive hypothesis that there's an epsilon NFA of the right form for E1 and ditto for E2. We add an epsilon arc from the final state of the automaton for E1, and that state, of course, then is no longer final, to the start state of the automaton for E2. The start state of the bigger automaton is the start state of the automaton for E1, and the final state is the final state of the automaton for E2. The new automaton is the concatenation of the languages of E1 and E2. Any path from the start to final state must first pass through E1. That is, it will do something like this. Then it will take this epsilon arc, and then it will do something E2. There's no other option because you can't get into or out of the green areas except as shown. Finally, here's the construction for star. Suppose we have an automaton for some expression E and we want to construct the automaton for E star. We add new start and final states, and the old final state is no longer final. There's an epsilon arc from the new start state to the new final state, so epsilon is always in the language of this new automaton. There are three other epsilon arcs as shown. The first of these epsilon arcs brings us to the start state for the automaton for E. We must traverse the automaton for E, following a path whose label is any string in the language of E. Now, when we reach the old final state of this automaton, we have a choice. Okay? If we follow the epsilon arc to the new final state, then we're done. We've found a path that has a label that is one string from the language of E. Or we have another option. We can go from the old final state back to the old start state, maybe take another path to there. Now we have a path that has a label that is the concatenation of two strings from the language of E. And we can go back again, take another path, make a label of that path would have now concatenation of three strings from E, and so on. We can do this as many times as we like, but then finally we go off to the final state, the new final state, and we are done with that. So this automaton really does have a language that's E star. You can go through the automaton for E 0 times by just going around it, or you can go through it once, twice, 3 times, as many times as you like. Now we're going to do the construction the other way. We'll start with a DFA and construct a regular expression defining the same language. The proof is inductive, and to make the induction work, we need to assume the states are named 1 through n. There's no harm in making this assumption, since the names of the states do not influence the language an automaton accepts. The induction is on the maximum number of a state that is allowed to be in the middle of a path, an idea that is explained on the next slide. We're going to talk about k-paths, which are paths that can go from any state to any state, but in the middle, that is excluding the endpoints, only states numbered k or less can be found. The inductive construction is on k, and it states that there is a regular expression whose language is the set of labels of all k-paths from state I to state j. We start with 0 paths as a basis, and by the time we get to n paths, there's no restriction on paths at all, so we have a regular expression describing the language of the automaton itself. Notice that an n path represents no restriction on paths at all, since there are no states whose names are higher than n. To get a regular expression for the language of the DFA, we take the union of the expressions for the n paths that describe how you get from the start state to each of the final states. For example, here's a little automaton. The 0 paths from state 2 to state 3 are the language of the regular expression 0. The reason is that we can only follow an arc from 2 to 3, and there's only one, the one that has label 0. That's the 0 describes the only path that gets us from state 2 to 3 without going through any other state. The 1 paths from 2 to 3 can go through state 1, but not through 2 or 3. Thus, we can still follow the arc from 2 to 3 labeled 0, but we also can follow the arc labeled 1 from state 2 to state 1, that's this, and from there the arc labeled 1 from state 1 to state 3. Notice that once we get to state 1, we cannot go back to 2 in a 1 path, and if we go to 3, we're finished. The path must end. The 2 paths from state 2 to state 3 are more varied. The only thing we cannot do is pass through state 3. Thus, from state 2, we can go to state 1 and back to 2 0 or more times. The labels along each such path is 1 0, so 1 0 star describes the labels we traverse by following this path any number of times, including 0 times. After oscillating as many times as we wish and winding up in state 2, we can then follow the 0 arc to 3. That's that part of the regular expression. These paths from state 2 to state 3 are described by the regular expression 1 0 star 0. That's this whole part. An alternative plan is to oscillate between states 2 and 1, winding up in 1. The labels of all these paths are described by 1. That is, you can go to state 1 for the first time, and then you can go 0 1 0 1 as many times as you like, including 0 times. Finally, though, you have to follow the path from 1 to 3, the arc from 1 to 3, in fact. And so 1 followed by 1 followed by 0 1 star followed by another 1 describes all those paths that start in 2, go from 1 to 2 several times, wind up in 1, and then go to 3. The regular expression for the labels of all 2 paths from state 2 to state 3 is the union of these 2 expressions that we have just described. The three paths from state 2 to state 3 also have a regular expression, but it is sufficiently complicated that we're going to save that example until we have seen the complete construction. Okay, now here's the induction of how you go from a DFA to a regular expression. Okay, the basis is k equals 0. Notice that a zero path can have no intermediate states at all. Thus, the set of zero paths from a state I to state j can only consist of a single arc, plus, in the special case that I equals j, no arcs at all. We can construct a regular expression for this language. Connect with pluses each of the labels, and in addition, if I equals j, then add an epsilon. So, for example, here's state I, here's state j, and suppose it has an arc labeled A, B, and C, then its regular expression is A plus B plus C. And if there's also an arc, let's say, from I to I, in addition, let's say that there is a loop with labels D and E on the state I, then the regular expression for the paths from I to I would be D plus E plus epsilon. We now need to introduce some notation. Let Rij super k be the regular expression for the set of labels of the k paths from state I to state j. We've really seen the basis case k equals 0. That is, Rij super 0 is the sum of the labels on the arc from state I to state j. If there's no such arc, then use the empty set symbol as the regular expression, but we add epsilon if I equals j. Okay, here's our example DFA again. Okay. R12 super 0 equals 0, since that is the label of the arc from the state 1 to state 2. And, of course, state 1 is not equal to state 2. Now consider R11 super 0. There's no arc from state 1 to itself, so we start out with the empty set. However, since the beginning and end states are the same, we add epsilon. Okay, and incidentally, notice that there's an algebraic law. That is, the empty set union anything is that other thing. So whenever you see an empty set symbol plus something else, you can just get rid of the empty set and the plus and just take what's left there. Now we shall do the inductive step, where we assume we've written all the regular expressions with super k minus 1, and we need to write the expressions for the k paths. A k path either never goes through state k at all, or it does so one or more times. That lets us write the expression for Rij super k in terms of expressions for k minus 1 paths. The first term covers the case that the k path doesn't even go through the state k once. That is, every k minus 1 path is a k path. All other k paths get to state k at least once. Thus we start out with Rik super k minus 1, which generates us the labels of all the paths that get us from state I to state k for the first time. Then comes Rkk super k minus 1 all starred. It generates the labels of all paths that go from state k to state k 0 or more times, with those paths not passing through any state k or higher. Finally, we concatenate with the language of the expression Rkj super k minus 1. That generates the labels of all paths from state k to state j that do not pass through state k or higher. Okay. Here's a picture of what a k path looks like with the vertical axis representing the state number. We've shown I and j above k, although they could be at any height. That is, for example, I could be down here, so could j, could be down there, or they could be higher. Doesn't matter. Okay. So one possibility is that the k path never goes through state k, or it could go through state k for the first time, but only through lower states. And from k to k, you could go, again, through lower states 0 or more times. And finally, you go from k to j through lower number of states, states numbered lower than k. And that represents all the paths that go from I to j through k and lower numbered states. Finally, as we have hinted, the regular expression with the same language as the given DFA is formed by taking the union over all final states j of Rij super n, where I is the start state. Okay. So here are our example DFA again. Now we have to install a start state and some final states. So let's assume that state 2 is the start state and 3 is the only final state. So the regular expression that we want is just R23 super 3. Okay, here's the expression for R23 super 3 in terms of the super 2 expressions. This expression is special because state 3 appears in two places as both k and j, and as a result we can simplify it as shown to R23 super 2 concatenated with R33 super 2 star. The reason is that if E is any regular expression such as R33 super 2, then E star E is the concatenation of one or more E's. Okay. Now we have another expression, R23 super 2, that you can think of as itself concatenated with none of the E's. Remember, E is actually R33 super 2. So this is R23 super 2 concatenated with no E's. This is R323 super 2 concatenated with E star E, that's one or more E's. So together you have R23 super 2 concatenated with 0 or more E's. And that's what this expression is saying. Again, remember E is R33 super 2. Okay, so we figured out what R23 super 2 is. We did that earlier, so let's just use it here. Okay. And here's an expression for R33 super 2. I won't give the details, but remember that this expression has to represent paths from 3 to 3 that never go through 3, so it could only jump from 1 to 2 and back again until it returns to 3. And here is the simplified expression composed of R23 super 2 and R33 super 2, that last being starred. So what you have at the end is a regular expression whose language is the same as the regular expression of this automaton in the corner. Each of the three types of automata, the DFA, the NFA, and the epsilon NFA that we discussed, and regular expressions as well, define exactly the same set of languages, the regular languages. That is, if you remember, we started with the DFA, and we showed that any NFA could be converted to a DFA, that's the subset construction. We then showed that any epsilon NFA could be converted to an ordinary NFA, that was sort of the closure construction. And earlier in this lecture, we showed that any regular expression can be converted to an epsilon NFA. And now we just showed that every DFA can be converted to a regular expression. That says any language defined by any one of these four notations is defined by all the others. Okay, we're going to finish up with a little discussion of the algebraic laws for regular expressions. We have several times argued that two different regular expressions represent the same language, and therefore one can be substituted for the other. Now, these are examples of the sort of algebraic laws that we find in the algebra of regular expressions, of arithmetic, Boolean algebra, and other algebras. The laws for regular expressions are not too different from those for arithmetic, but we have to be very careful to observe the differences. First, plus and concatenation behave almost like plus and times for arithmetic. The plus operator, which remember is set union, is associative and commutative just like addition. Remember also that the commutative law says that x plus y equals y plus x. That is, the order of the arguments doesn't matter. Okay. The associative law says that you can group the operator in any order, or formally x plus y grouped plus z equals x plus the grouping of y plus z. That is, you can apply plus to the first two arguments first, or apply it to the last two arguments first. It doesn't matter. The result is the same. Concatenation, like multiplication, is associative. Moreover, concatenation distributes over union just like multiplication distributes over addition. That is, x concatenated with y plus z equals xy plus xz. That is, x, y plus z equals xy plus xz. That's the distributive law. Okay. The big difference between regular expressions and arithmetic is that concatenation is not commutative, although multiplication obviously is. That is, the regular expressions AB and BA don't denote the same languages. That is, the first, AB, just denotes the language that contains the string AB, while the second, BA, denotes the language that contains only the string BA. Okay. Arithmetic also has certain constants that serve as identities for addition and multiplication. Obviously, 0 is the identity for addition, and that adding 0 to any number gives you that number back. Likewise, 1 is the identity for multiplication, because multiplying any number by 1 gives you that number. Finally, 0 is also the annihilator for multiplication, because multiplying any number by 0 gives you 0. Union and concatenation have analogous identities. As we shall see, the identity for union is the annihilator for concatenation, just like the identity for addition is the annihilator for multiplication. Now, the identity for union, as we actually have mentioned, is the empty set. Obviously, taking the union of the empty set with any set yields that set. The language containing only the empty string is the identity for concatenation. Concatenating any string s with the empty string yields s, so concatenating the language represented by the regular expression epsilon with any other language, say the language represented by regular expression r, will result in the same language, the one represented by r. Finally, the empty set is the annihilator for concatenation. That is, if we take any language, say the language represented by regular expression r, and concatenate it with the empty language, we get the empty language. Why? The result of the concatenation requires that we take strings from both languages and concatenate them in all possible ways. But you can't find any strings in the empty language to use in the concatenation of strings. Today we're going to give some hints about how regular expressions are used in practice. I'm going to mention some of the extensions that are found in various Unix commands. I'll also talk about some specifics of text processing algorithms and concentrate on the important task of lexical analysis, that part of a compiler that looks at the entire program being compiled and breaking it up into tokens, which are sequences of characters that logically belong together. Many systems use regular expressions of some sort to describe patterns. Often these are embedded in the proprietary code of a company, but there are also some quite visible ones, such as a number of Unix commands. I'm going to tell you one particular story involving proprietary software before moving on to generalities regarding text processing. Jungli was a startup founded by 3 of my PhD students and 2 others in 1994. At the time, the web was really new, and they had the idea of building systems to integrate web pages into more useful products. They were doing that for about 2 years when they got a contract from Yahoo to build a facility that would let Yahoo visitors search for books and get a table giving the price, delivery charge, and delivery delay at different booksellers. Immediately upon deployment of that product, Amazon bought Jungli in order to shut down the comparison shopping capability. Interestingly, Amazon did not understand that I bought from them not because they were the cheapest, but because I was confident that they would deliver what I asked for and deliver it on time. And apparently I was not alone in that thinking, but the world of online commerce was new, and Amazon could not be sure of the impact of automated comparison shopping. An interesting sidelight, Amazon actually got good value for Jungli because one of its founders, Anand Rajaraman, while at Amazon, was the inventor of Mechanical Turk. But the first paid work that Jungli got was a contract from the Washington Post to produce an online table of the employment opportunities offered by companies that were placing print classified ads at the Post. This job was not trivial. Jungli had to go to several hundred websites and extract the information about each job automatically. If you look at one site, you can probably figure out how to do it, which links to follow from the home page to get to the employment pages, and once there, how to navigate in the HTML source text to find the critical information about the job, such as the title and salary. But you need to do this for each site, and to make matters worse, the Jungli guys discovered that these sites were evolving. That is, not only the jobs changed, but the structure of the pages or even the whole website changed. The result was that approximately once a week, the reader for any given site would break and have to be redesigned. So the Jungli guys developed a regular expression language for describing how to navigate a website to extract the information they needed. The input symbols were the usual characters such as letters, so they could look for important words like salary. They also treated HTML tags like OL, that is this, as input symbols because they gave important hints about the page structure. For instance, a page might say, send salary requirements to, but that doesn't indicate the salary for a particular job. But when you get to a list of jobs, and that is indicated by the ordered list tag, that's the OL, and only after that does salary mean that the number following is a salary for a job. Another important kind of input element is a link, which indicates that it's necessary to move to another page. Once this regular expression language was implemented, it was easier to write regular expressions to find key information like title and salary than to write the code to process web pages directly. Thus, there was an increase in productivity as they added sites to their database. Moreover, when the site changed, it was relatively easy to modify the regular expressions to track the changes in the site. The architecture of the system developed at Jungli appears in many places. The input language is regular expressions plus actions, which are arbitrary code that is executed when the regular expression is recognized. In this case, the actions would be things like return this integer as a salary. The regular expression is compiled into a DFA or sometimes into an NFA that is simulated, effectively by executing the lazy version of the subset construction as needed. The simulation of the DFA or NFA goes on exactly as we have described it theoretically. Each input symbol causes a state change and nothing more. The magic happens when an accepting state is reached. Then the associated action is executed, and this action allows the regular expression processor to interact with the rest of the world in some useful way. We're now going to talk about the Unix extensions to regular expressions. There are many commands in Unix that have some sort of regular expression notation for input. An important example is the grep command, which stands for Global Regular Expression and Print. Most of the regular expression-based languages, even though they have extensions to the notation we've covered so far, define only regular language. There are also some commands that have additional extensions that allow non-regular languages to be recognized, but we're not going to go into these features. Incidentally, it is no coincidence that regular expressions figure heavily into the original Unix commands. Before he did Unix, Ken Thompson had worked on a system for processing regular expressions by converting them only as far as an NFA and simulating the NFA in code. We're now going to meet some of the Unix extensions to regular expressions. You can put brackets around any list of characters as a shorthand for the same characters connected by plus signs in the notation we have used until now. You can also describe a sequence of symbols that are consecutive in the ASCII order of characters by giving the first character a dash and then the last character. For example, A-Z, that's this, stands for any lowercase letter because the lowercase letters have consecutive codes in ASCII. You can represent any letter by putting dashes between lowercase a and z, and the same for uppercase. That's this. Okay, notice that the upper and lowercase letters are not consecutive in ASCII, so you cannot represent these 52 characters with a single range. Incidentally, as we see, characters like brackets and dash have special meanings in Unix regular expressions. So if you want to use one of these characters as itself, you need to precede it by a backslash. So for example, slash left bracket is a real left bracket. It's not the left bracket that you find in range expressions. And the character dot or period is shorthand for any character. Here are some more Unix changes to the regular expression notation we learned. Okay. The union operator is actually represented by a vertical bar instead of the plus. But the plus symbol is another operator used like star and meaning one or more. That is, in the Unix notation, E plus, that's that, is shorthand for E concatenated with E star. So for example, A-Z all plussed means one or more lowercase letters. The question mark operator is also used like star but means 0 or 1 of. That is, E question mark is shorthand for E plus epsilon. So, for example, AB in brackets question mark means an optional A or B. We would write it in our original notation as A plus B plus epsilon. You may remember our DFA example for recognizing strings that end in ing. It involved a lot of explanation as we considered where to go from each of the states that represented some progress toward finding ing. However, there is an easy regular expression for the same language using the Unix dot. It's just dot star ing, like that. Okay. Or even if we didn't have the dot in our notation, we could simply replace it by all the legal input symbols connected by pluses. In fact, it's even much easier to design an NFA for this language than it is to design a DFA. Okay, here is an NFA. Essentially, it guesses when it has seen the I that begins the final ing. Thus, even on an input like the first I in skiing, it can remain in the start state. That is, it can go from the start state to itself on an I if it likes. And in fact, it always does like, because the NFA always does everything. Okay, it can remain in the start state on the first I and then only travel to the right, that is here, on the second I. There's no need to worry about what to do in a state like one that represents the discovery of I and N. Where do you go if the next input is not G? It doesn't matter, because you'll still be here, and another sequence of states will get you where you actually need to go. Now let's talk a little bit about lexical analysis, the breaking of an input program into its basic units called tokens. For example, every identifier in a program is a token. Likewise, the reserved words like if or while are tokens. Many single characters are tokens by themselves. In typical programming languages, semicolon is a token used for separating statements, plus is a token indicating addition, less than is a token by itself indicating the less than comparison operator. There are also multi-character operators such as the less than or equal sign, which together indicate the less than or equal comparison. There are tools like Lex, or its open source version Flex, that let you write a regular expression for each token. You can also provide a piece of code as an action to be executed when an instance of that regular expression is recognized. For example, the code for when an integer is found, might simply return that integer. As an example, the expression for identifiers might be the one shown here. That's this. Using the Unix notation, this expression describes identifiers as any letter, that's this, followed by 0 or more, the star, letters or digits. In many languages, identifiers allow some more options. For example, underscore might be included as if it were another digit, so it would just appear in this list here as an underscore. In Lex, you write an action, which is an arbitrary code to be executed when the regular expression for a token is matched. In the simplest cases, all this code does is return an integer code representing the token found, but the action might be much more complicated. For example, if an identifier is found, the action might involve installing that identifier in a symbol table where all identifiers used by the program are stored. When building a lexical analyzer using regular expressions for the tokens, there are some resolution of ambiguities that need to be faced. Two examples are illustrated here. For one, reserved words like if also match the expression for identifiers, but if is not a legal identifier, so we have to make sure the lexical analyzer does the right thing on if. Okay. For another, when we see less than, we don't immediately know if it's a token by itself or part of a larger token, which would be less than or equal in this case. We need to make sure we don't prematurely declare victory and return the less than when less than or equal is intended by the programmer. Okay. A good architecture for building a lexical analysis code from regular expressions is to start by converting each regular expression to an epsilon NFA. Each of these epsilon NFAs has its own final state with which the action for that regular expression is associated. We combine all these epsilon NFAs by introducing a new start state. The start state has epsilon transitions to the start states for each of the NFAs. Okay. Looks something like this. Here's the new start state. Here are all the old start states and their automata. And we just put transitions on epsilon to each one of them. Okay. All the final states of the NFAs remain final, and they each have their associated actions. So, for example, these are all final states. An NFA can have several final states, in fact. After that combination, we convert to a DFA, or perhaps an NFA without epsilon transitions, which we will then simulate. Okay. We need to give the regular expressions an ordering, and this ordering determines the priority among actions. A typical ordering puts all the reserved words ahead of identifier, so that way, if the DFA discovers that the next token is if, it in principle does not know whether to execute the action for the reserved word if or for identifiers or both. But the fact that if takes priority over identifiers says that this token should be treated as a reserved word and not as an identifier. However, to make all this work right, the DFA actions need a special ability. The ability to take an input symbol it has read and put it back at the front of the input stream. That input will then be read again, typically the next time the lexical analyzer is told to look for the next token. Here's an example of why the ability to restore an input symbol just read back to the front of the input is important. Suppose the lexical analyzer is told to find the next token, and the first character it reads on the input is the less than symbol. It has to read the next input, and if that input is an equal sign, then we can be sure the token is less than or equal. Okay. But if the input is anything else, for example a blank, a letter, or a digit, then that character must be put back on the input and less than by itself declared to be the token. For another example, if the lexical analyzer has read the characters I and F in its quest for a token, it might have seen the reserved word if. But we won't know until it reads the next character. If that character is a letter or a digit, anything that can extend that identifier, then we do not have the reserved word if, we have a longer identifier. However, if the next character is not one that can extend an identifier, such as a blank or a left parentheses, then we really do have the reserved word if. In that case, the next character must be pushed back onto the front of the input. Today we're going to discuss algorithms for answering questions about regular languages, or really about the representations for the languages, such as finite automata. The questions we can resolve for finite automata include many we cannot resolve for programs in general. Examples include whether a given string is accepted by a given automaton, that's the membership problem, or whether a given automaton accepts any string at all, the emptiness problem. As part of our discussion, we're going to prove an important theorem called the pumping lemma that lets us show certain languages not to be regular. Automata theory talks about many different classes of languages, including context-free languages, recursive and recursively enumerable languages. We're going to meet each of these classes, but for the moment we know only one class, the regular languages. When we investigate a class of languages, there are two important issues. The first is decision properties. We shall see that there are many questions we might like to ask about a language, or rather its representation, such as whether it is empty, finite, or infinite. It is good to know there are algorithms to answer such questions, at least for the regular languages. Unfortunately, as we meet larger classes of languages, we find that in general, the larger the class of languages, the less likely there is to be an algorithm to answer a question about languages in that class. The second important issue is closure properties of the class. These involve applying operations such as union to languages in the class. We're going to defer the discussion of closure properties to another lecture, although I'll give you an example on the next slide. Closure properties are statements that when we apply certain operations to languages in the class, the result is also in the class. For example, we say that a class of languages is closed under union if given two languages in the class, the union of those languages is also in the class. So if I have two regular languages, I can represent them by regular expressions and connect those expressions by a plus with the appropriate parentheses to get a regular expression for their union. Similar constructions work for their concatenation and closure. Now let us address the main topic of this lecture, decision properties of regular languages. We've used both formal and informal ways of describing languages. The formal ways include finite automata and regular expressions, each of which defines a language by a precise mathematical definition. But we have also described languages informally by prose statements and set formers, such as this, or even more informal statements like this. Okay. However, you can't answer questions about a language unless you have a formal description. For instance, we will talk shortly about testing whether a regular language is infinite given one of its formal representations. It looks like the last of the informal descriptions describes an infinite set, but does the word some mean any, or some one particular number like 10, for example, that I have in mind? Thus, we're only going to use formal descriptions of languages when we talk about algorithms for deciding things about those languages. Thus, a decision property for a class of languages is an algorithm that takes a formal representative of the language. The algorithm answers some particular question about the language, such as whether or not the language described by the representation is empty. Here are a few examples of why we might be interested in decision properties of regular languages. Both involve protocols represented by automata. If we ask whether the language of such an automaton is finite, we are in effect asking whether the protocol it represents is guaranteed to terminate. Or if we make the final states of the automaton be error states, then asking if its language is empty is tantamount to asking whether the protocol can fail. And remember, we couldn't answer either of these questions about programs in general, so we couldn't get the answers to these questions about protocols by looking at the code that implements them. Another use for decision properties of regular languages involves minimizing their representations. For instance, DFAs are a good representation for certain kinds of digital circuits, those that have memory. We usually want the smallest circuit to accomplish a task, and a good first step is to find a DFA that does what we want and has the smallest number of states of any DFA for the same language. It turns out that we can tell whether two DFAs are equivalent, that is, whether they define the same language. That lets us find a minimum state DFA equivalent to any given DFA. Again, we could do none of this for programs in general. We can't tell whether two programs do the same thing, and we can't find a smallest equivalent for a given program, even though we know in principle that one must exist. The membership question for regular languages is answered by an algorithm that takes a DFA and a string and tells whether or not the string is accepted by the DFA. The algorithm is the obvious one. Simulate the DFA on the input. Here's an example. It's something we've seen several times before. Each time I show it to you, I use a different style of presentation, but the idea is always the same. Here is the DFA for strings without consecutive ones, something which I know we've seen before. And the input string is 0, 1, 0, 1, 1. That obviously has consecutive ones, so it shouldn't be accepted. Well, let's see what happens when we simulate it. We read a 0, we stay in A. When we read a 1, we go to B. Read a 0, we go back to A. Read a 1, we go to B. Read another 1, we go to C. When we simulate this DFA on the input, we see that indeed the string gets the automaton to state C, and it is not accepted. Now you might wonder, what if the regular language were represented by an NFA or a regular expression, for example? Then you first need to convert the representation to a DFA and then simulate the DFA. It is possible to convert from any of the four representations we know about to any of the others using this circle of conversions. So doing might exponentiate the size of the description, but there is still an algorithm to do the conversion, and that's all we need to show there is, for example, an algorithm to tell, given a regular expression and a string, whether the string is in the language of the regular expression. Generally, proofs of closure or decision properties require either a DFA or a regular expression, by the way. The emptiness problem is, given a representation for a regular language, does its language contain any string at all? Okay, we're going to assume the language is represented by a DFA. Obviously, if by some other representation, then convert it to a DFA. Finding reachable states requires a breadth-first or depth-first search from the start state. I'm not going to assume you are familiar with these search techniques, but it is fairly easy to think of some way of searching a graph from a single node by following all arcs out of the node and marking those nodes you have visited. Then, follow arcs out of the nodes you visited and mark any other nodes you visit. Keep doing that until you cannot mark any other nodes. The marked nodes are those that are reached from the start state on some input. If at least one final state is marked, then the DFA accepts at least one input. If no final state is marked, then it is impossible for the DFA to accept anything and its language empty. Here is an example. Here's your start state. We might mark these guys, maybe mark these guys as we go. But if all your final states are out here and never get marked, then obviously, no matter how complex this automaton is, you can't reach a final state and you can't accept anything. Now, if you have an automaton with 3 states, it's pretty easy to tell what's reachable and what isn't. But if you have 1,000,000 states represented by some table, then it is hardly easy to tell. But fortunately, we have a straightforward search algorithm regardless how large the automaton or graph is. Now let us take up a more difficult problem, but one that we can still solve. We'd like to know whether or not the language defined by a DFA is finite or infinite. The first fact we're going to prove is that if the language of the DFA contains any string of length n or more, where n is the number of states of the DFA, then the DFA contains an infinite number of strings. Surely, if the DFA doesn't accept any string of length equal to or greater than n, then it accepts only a finite number of strings. However, it doesn't seem feasible to test membership for all input strings of length n or more, since there are an infinite number of them. Can we ever finish? If not, then we really don't have an algorithm for testing infiniteness. But as we shall see, it is possible to limit the length of strings we have to test to twice the number of states, so we have a really large and ugly but finite task, and we really do have an algorithm. So let's try to prove the point we need, that if the DFA accepts any string whose length is at least the number of states n, then it accepts an infinite number of strings. First, observe that a string of length n or more has at least n plus 1 states along its path. For example, a string of length 2 has 3 states on its path. Here is a typical picture we might have. String AB looks like that. Notice, no matter how many, well, the number of symbols in the string is the number of arcs, and there's always one more node than there are arcs in the path. That's why there will be n plus 1 states for a string of length n. Okay. Now, if there are only n different states, and there are n plus 1 states along the path, then 2 states along the path must be the same. That's called the pigeonhole principle, you might remember. Here's a picture of the path for string W, which we're breaking up as x, y, z. X is the prefix of W that gets the DFA to the first state that repeats on the path, which we call state Q. It's right here, of course. Then Y is the part of W that gets the DFA back to Q for the first time. That is, the end of Y is the second occurrence of Q. Notice that therefore Y cannot be the empty string, although X or Z might be. Finally, Z is the rest of W, and we know it gets the DFA to a final state because W is accepted by the DFA. Notice that the path labeled Z may have states that also appear earlier, but it doesn't matter. The important thing is that we identified the first repeating state Q. We claim that X, followed by I repetitions of Y, followed by Z, is also accepted by the DFA for any integer I. To see why, X takes us to state Q, so we could, for example, go like this. Okay. And then we could skip Y altogether, just follow Z, and we get to a final state. That tells us that XZ is in the language. Or we could follow X to state Q. We could go around loops many, many times, and then finally go off following Z, and again get to the final state. Or after I uses of input Y for any I, however large, we follow input Z and we accept. This proves that X, Y to the I, Z is accepted for any I. Remember that Y cannot be empty, so all these accepted strings are different. Thus the DFA accepts an infinite number of strings, one for each I. Remember, we still do not have an algorithm because we can't test the infinite number of strings of length equal to or greater than n. However, we don't have to, because it is sufficient to test strings of length between n and 2n minus 1, and there are a finite number of such strings. When we prove this statement, we shall at least have an algorithm, although it is a rather time-consuming one. Now, we picked Y to be the first cycle on the path, so the length of xy cannot be greater than n. That is, some state within the first n plus 1 states on the path surely repeats. We also know that if the length of y is at least 1, so y lies between 1 and n, then if w is the shortest accepted string of length at least n, then we claim that w cannot be as long as 2n. For suppose it were. Now xz, as we know, is another accepted string, and the length of xz is the length of w minus the length of y, and the length of y is at most n. So the length of xz is at least n. That means that xz is a string shorter than w, yet at least n in length, and it's also accepted. But we assume that there was no string accepted that was shorter than w and also of length at least n. As a result, given any really long string w that's accepted, we can keep taking out pieces of length between 1 and n, that's the y in each of these diagrams, and we just keep throwing them away, and eventually what's left of w will be between n and 2n minus 1. So the algorithm to decide whether a regular language is infinite is to construct a DFA for it, and let the DFA have n states. Test all the strings of length between n and 2n minus 1 and say infinite if any of them are accepted. Otherwise, say finite. This is a terrible algorithm. If there are k input symbols and n states, then the number of strings we have to simulate is about k to the power 2n. That is a lot of work, and there is a much more efficient algorithm, one that takes time proportional to the number of transitions, that is k times n, if implemented right. I wanted to give you the argument about the lengths of strings because it's important when we take up the pumping lemma, a technique for showing languages not to be regular. However, let's sketch how the efficient algorithm would work. We already discussed searching forward from a node in a graph to find all the nodes you can reach. So we can eliminate the states that are not reachable from the start state. We then want to eliminate states that don't reach a final state. This algorithm is the same, except start by marking the final states and follow the arcs backwards. Now there's an elegant algorithm for finding cycles using depth-first search that takes time proportional to the number of edges or transitions. I'm going to trust that you will meet this algorithm in a course on algorithms and data structures if you haven't already done so. However, here is a simple way to test for a cycle in a graph. It takes time proportional to the number of nodes or states times the number of arcs or transitions. We're going to do the same thing for each node n. Starting at n, search forward until you either can reach no more nodes or you discover that you can reach n. That is, here's node n, we explore forward from it, and if we're lucky, at some point we reach a node that has an arc back to n. Okay. If you can reach n, then you have a cycle and we can conclude the language of the DFA is infinite. If not, try the same process from another node. If you exhaust all the nodes as starting points and you still haven't found a cycle, then there are none and you conclude the language is finite. This is a good time to introduce the pumping lemma for regular languages because we have essentially proved it during our analysis of the infiniteness problem. Here's the statement of the pumping lemma. For every regular language L, there is an integer n, which happens to be the number of states of some DFA for L, such that for every string w in L whose length is at least n, we can break w into w equals x, y, z, where y is the label of the first substring of w that goes from a state to the same state, as we saw in the previous slides, such that three things are true. First, the prefix xy of w is short. It is of length at most n. We assure that by making y be the label of the first cycle we encounter. Second, y is not the empty string. We assure this because y connects two different occurrences of the same state along the path of w. And lastly, x, y to the I, z is in L for all integers I. This statement is particularly complex because it is of the form for all there exists for all there exists. But here's how we use it. Think of a game played between you and an adversary. You pick the language L that you want to show is not regular, and suppose the adversary claims it is regular. Then the adversary has to provide the there exist parts while you play the for all parts. You've already picked L. Now the adversary has to pick n. He can pick a number as large as he likes, but once picked, it is finalized and the game proceeds. Now you get to pick the string w, subject only to the constraint that it is at least as long as n, the number the adversary picked. Next, the adversary has to break your w up into x, y, z, subject to the constraints that the length of x, y is at most n and the length of y is at least 1. You win the game by picking an I such that x, y to the I, z is not in L. However, in a proof, we don't know what moves the adversary will make. Thus, to win, we need to cover all possible moves. That is, we know the picked n, but we don't know n's actual value, so we must pick w in terms of n. Similarly, we know w equals x, y, z, but we don't know exactly where y is, except that it is not empty and it is among the first n positions of w. Thus, our argument that x, y to the iz is not an L must work for any of these possible y's. Now, let's see an example. Let us pick this language as L. It is the set of strings consisting of some number of zeros followed by the same number of ones, and we have claimed before that it is an example of a non-regular language. Now we're going to prove it. Now the adversary picks n. We don't know what n is, but we know it has some fixed value. Now we get to choose w in terms of n. And we pick w equals 0 to the n, 1 to the n. That is n zeros followed by n ones. But then the adversary gets to break w into x, y, z, and we don't know exactly how it is broken. But we know enough about x, y, z to show that there is some string, in particular the case I equals 2, that the pumping lemma says has to be in the language L. But obviously it isn't, because it has more zeros than ones. That is, we know that y, being part of the first n positions of w, can have only zeros. Okay, so two y's have more zeros than one y, and the number of ones, which are all contained within z, doesn't change. We next take up the question of testing whether two regular languages are the same. We suppose we're given representations for two languages, L and M. Whatever representation we're given, we convert to DFAs, and then we have to combine those DFAs into a single DFA that in a sense runs both DFAs in parallel. We call it the product DFA. Suppose these two DFAs have states Q and R. In the product DFA, the states are pairs, one state from Q, the other from R. The start state of the product DFA is the pair consisting of the start state from each DFA. For the transitions of the product DFA, suppose we have a state that is the pair QR, and suppose A is the input symbol for which we want to figure out the transition. We look at the transition function for the first DFA, say delta L, and we see where Q goes on input A. So here's Q, and on input A it goes to some state like that. Then we look at the transition function for the second DFA, say delta M, and we see where R goes on input A. So here's R on input A, it goes somewhere here. Okay. Then in the product DFA, the transition from the state QR on input A is to the state pair that is whose first component is delta L of QA and whose second component is delta M of RA. That is, we simulate the two transitions in parallel. Here's a little example. Here are the two given DFAs. We'll call this the orange DFA and that the purple DFA. And here's the product DFA. It's obviously here. For example, let's figure out the transition from AC on 0. So here's state AC, and I look in the orange automaton, A on a 0 goes to A itself, and in the purple automaton, C on a 0 goes to D. So the combination AC goes to AD, and you see that transition here. For another example, where does AD go on input 1? Well, the orange automaton says A goes to B on 1, and the purple automaton says D goes to C on 1. So on 1, AD goes to BC. That's this transition there. The algorithm for testing whether two DFAs are equivalent, that is, whether they accept the same language, begins by constructing the product DFA. make the final states of the product DFA be all those pairs such that one is a final state and the other isn't. If string W reaches one of these final states in the product, then W is accepted by one of the original DFAs and not the other. Thus, the two languages are not the same. Only if the product DFA with this selection of final states has an empty language are the two DFAs equivalent. Here's an example. AC is made a final state because in the original automata, C is final and A is not. Likewise, BD is final because B is final, but D is not. We now see that the two original DFAs are not equivalent. It happens that the final state BD is not reachable from the start state, so there are no strings that the orange automaton accepts, but the purple one does not. However, AC is also a final state, and it is obviously reachable from the start state because it is the start state. That is, the empty string distinguishes between the two automata. The empty string is accepted by the orange automaton, but not the purple one. A related question to ask about regular languages is whether one is contained in the other. The test is in a sense one half of the equivalence test we just saw. Start by building the product automaton. But we have to define the final states differently. How would you do that? That is, L is not contained in M if and only if some string W that is in L is not in M. Such a string would get the DFA for L to a final state, but would not get the DFA for M to a final state. So the question of containment is the same as the question of whether there is any string W that gets the product automaton to a state QR where Q is final and R is not. Here, B is the only final state of the first automaton, and D is the only non-final state of the second automaton, so only BD is final. Okay. As we observed before, BD is not reachable from the start state. It has arcs out, but no arcs in. Thus, the language of the product automaton is empty, and we conclude that the language of the orange automaton is a subset of the language of the purple automaton. Next, we're going to attack the problem of, given a DFA, find the equivalent DFA with the fewest states. There is an obvious dumb algorithm. Just consider all the DFAs with the same input alphabet, but a smaller number of states. There is a huge but finite number of such automata, so in principle we can solve this problem. This time we're not going to dwell on the bad algorithm. We'll talk you through the good algorithm immediately. The key idea is to build a table of pairs of states and figure out which pairs are distinguishable, in the sense that there is some input string that leads one of the pair to a final state and the other to a non-final state. Otherwise, states are indistinguishable and they can be merged into a single state. Here's the tennis automaton we saw way back at the beginning of the course. Now, let's look at the states 40, 30 here and add in. Input S takes them both to an accepting state, that is, server wins, and input O takes them both to deuce, right, here and here. Thus, no further inputs could ever distinguish 40, 30 from add in. Similarly, 30, 40 and add out are indistinguishable. Now we can deduce that 30 all, that's here, and deuce are also indistinguishable. On input S, they go to 40, 30 and add in, respectively. That is here, 30 all goes to 40, 30 on S, and deuce goes to add in on S. But we know that those two states are indistinguishable, so we'll never be able to distinguish 30 all from deuce by a sequence beginning with S. And further, on input O, well, 30 all goes to 30, 40, and deuce goes to add out, and we said we can't distinguish these two states. So there's no string whatsoever that can distinguish 30 all from deuce. Okay, we're now going to talk about how we find the distinguishable states. The basis is pairs that are distinguishable by the empty string. These are the pairs that have one final and one non-final state. For the inductive step, we can mark a pair QR if these states go at some input A to distinguishable states. That is, say here is Q, and on A goes to some state. I don't know what it is, but it's certainly delta of Q and A. And here's R, and it goes on A to, again, some other state. I don't know what it is, but it's a delta of R and A. And then these two states on input W, we'll say that this one goes to a non-final state, and that goes to a final state on input W. Okay. Then I claim AW distinguishes Q from R, because obviously Q goes on AW to a non-final state, and R goes on the same AW to a final state. After no more marks are possible, the unmarked pairs are equivalent and can be merged into one state. This point may be obvious, but we're going to need it in what follows. If there's no string W that distinguishes states P and Q, and there's no string that distinguishes Q from R, then how could some string W distinguish P from R? That would mean that there's some string W leads one of P and R to a final state and the other to a non-final state. Let's say R leads to a final state. So here's W leading P to a non-final state, and here's R, and on the same W gets to a final state. But then W also distinguishes Q from either P or R. So here's Q, and W leads it to some state. Okay, so let's say that W leads Q to a final state. Then W distinguishes Q from P, because here P on W goes to a non-final state, Q on W goes to a final state. Okay. If Q goes to a non-final state, then it doesn't distinguish P from Q, but it does distinguish R from Q, because Q would then go to a non-final state while R goes to a final state. Incidentally, distinguishable is not transitive. It is quite possible that W distinguishes P from Q and also Q from R, but does not distinguish P from R. For example, W could lead both P and R to final states and Q to a non-final state. We're not going to use the table of indistinguishability to merge states that are indistinguishable. That gives us the minimum state DFA, although we must be careful to remove at some stage all the states that are not reachable from the start state. Okay. Suppose we have a set of indistinguishable states, say Q1 through Qk. We're going to replace them all by a single state that behaves as they all do. Call the representative Q. It can be one of the Qi's or some new name we create for this purpose. On any symbol A, all the indistinguishable states, the Qi's, go to states that are also indistinguishable from one another. For if not, then we could use a distinction between, say, the states delta Q1 of A and delta Q2 of A to distinguish between Q1 and Q2. But we already know that Q1 and Q2 are indistinguishable, so that can't happen. Thus, make the transition for state Q on input A be the representative for the indistinguishable states delta Q1A and so on. Let's work with the DFA that we constructed from the NFA that represented the moves on a chessboard. We're going to make it easier to work with by renaming the states to be single letters. For example, A is the set containing only 1, and G is the set containing 1, 3, 5, 7, and 9. Here is a little trick for arranging pairs in a triangle so each pair appears exactly once. Notice that the rows are the states in order except for the last state G, which doesn't appear there. Then the columns are labeled by the states in backwards order except for the first state A. We begin the table of indistinguishabilities by marking each pair that consists of a final state and a non-final state. Here the final states are F and G, so pairs that have one of these and one of the other states, A through E, are marked. Let's look at the transitions on input R. Notice that the column for R has only states B and D. Since we have not yet distinguished B from D, there is no way input R can help distinguish other pairs of states at this point. However, we have more luck with input B. Some states go to final states on input B, namely C, D, E, and G, and the others, A, B, and F, go to non-final states. Thus, we can distinguish any of C, D, E, or G from any of A, B, or F. Some of these pairs are already distinguished, but we get 7 new pairs marked in red here. At the next step, we discovered 2 more distinguishable pairs, CD and CE. For example, C and D lead to F and G respectively on input B. So we know that whatever string W distinguishes F from G, B followed by W will distinguish C from D. Now we can mark the pair AB. These states transition on input R to B and D respectively, and we already know we can distinguish B from D. Unfortunately, D and E can never be marked because on both inputs they go to the same state. Okay. We are now done. We've distinguished every pair of states except for D and E. Moreover, we can never distinguish these states since they both go to D on input R and to G on input B. Thus, D and E form an indistinguishable group of states, and we can replace them by a representative. We choose the new state H as the representative, and all transitions from other states to D or E are replaced by transitions to H. The rows for D and E are replaced by a row for H. As D and E transition to D on input R, H transitions to itself on R. The transition on input B for H is to G, which is the same as it was for both D and E. As we mentioned, collapsing indistinguishable states to a single state goes a long way to finding the minimum state equivalent to a given DFA. But there is one other issue that indistinguishability doesn't address: the possible existence of unreachable states that are cluttering up the transition diagram or table. But it is easy to find such states, and we can either eliminate them from the original DFA, or we can eliminate them after merging indistinguishable states. It doesn't matter. Now we've done our best to combine states that we know how to combine, but it is in principle possible that there is some other smaller DFA that we can't get by combining states of our DFA, and fortunately, that can't happen, as we shall now see. Here's the proof that there is nothing smaller than the DFA we get by merging states and eliminating unreachable states. Suppose A is our DFA and B is a hypothetical equivalent with fewer states. Okay. Imagine we combine the states of A and B to form a larger DFA. It doesn't matter what the start state of the combined automaton is, but the final states are those of A and B. We need to use distinguishable in its contrapositive form. That is, if W distinguishes delta of QA from delta of PA, then surely AW distinguishes Q from P. So if Q and P are indistinguishable, then so are their successors on any input A. Here's an informal illustration of the proof technique. We start off with the fact that the start states of automata A and B are surely indistinguishable because the automata accept the same language. Now suppose the start states go to some states P and Q on input A. P and Q must be indistinguishable because if they were distinguishable, then we could distinguish the start states, and we know we cannot do that. Now, suppose Q and P go on input B to two other states, R and S. Then R and S must be indistinguishable for the same reason. Formally, we shall prove that every state Q of A is indistinguishable from some state of B. The proof is an induction on the length of the shortest string that gets you to Q from A's start state. Notice that because we eliminated unreachable states, we know there is such a shortest string. For the basis, the state of A that is reachable from the start state by a string of length 0, which is of course the start state itself. We know that this state of A is indistinguishable from the start state of B because the languages are the same. For the induction, assume the inductive hypothesis for strings shorter than W, and suppose W is a shorter string getting A to state Q. Let W equal XA, that is, A is the last symbol of W and X is all the rest of W. We can apply the inductive hypothesis to X because it is shorter than W. We know X gets A to some state R that is indistinguishable from some state P of B. But then A takes state R on input A to state Q, and we know B takes state P on input A to some state, say, S. Then Q must be indistinguishable from S using the argument that we saw 2 slides ago. Now, we use the transitivity of indistinguishable to argue that no 2 states of A are indistinguishable from the same state of B. For if they were, they would be indistinguishable from each other. But A cannot have indistinguishable states because we merge them all constructing A. Thus, B has at least as many states of A, even though we started off assuming that there was no relationship between the automata A and B, except that they each accepted the same language. So that concludes the entire argument. It says that by throwing away unreachable states and then merging indistinguishable states, you get an automaton that is as small, that is, has as few states, as any other automaton for the same language. Today's topic is closure properties for the regular languages. We should recall that a closure property is a statement about a certain operation on languages that says when the arguments are languages in the class, then so is the result. You can see on the title slide the list of closure properties for the regular languages that we are going to discuss. Our first closure property will be union. That is, if L and M are regular languages, so is L union M. To prove this fact, we use the regular expression, say R and S, whose languages are L and M respectively. We know L and M have regular expressions because they are assumed to be regular languages. Then R plus S is also a regular expression, and we know its language is the union of L and M. The same idea works for concatenation and closure. Remember to draw parentheses around R and S if they are needed, like this. For example, if R is 0 plus 1, and S is 0, then you need to write the expression with parentheses around the 0 plus 1. Otherwise, you'll get the wrong language. You don't need the parentheses around the 0. Regular languages are also closed under intersection. For intersection, we can't use regular expressions very easily, but the DFA is perfect for proving closure under intersection. So we take DFAs A and B for the 2 languages whose intersection we want, and we construct the product automaton. The final states in the product are those states that are final in both of the given automata. Thus, the product accepts an input string if and only if both of the original automata do, and that's exactly what we want for intersecting the languages. Here's an example based on the same product automaton we used last time. The only final state in the product is BC. That's this, of course, because B and C are the only final states of their automata. B and C are there. Here's an example of how closure properties prove useful. Okay, remember we proved using the pumping lemma that L1, the set of strings of zeros followed by an equal number of ones, is not a regular language. L2, the set of all strings with an equal number of zeros and ones, isn't regular either. However, suppose L2 were in fact regular. Then since regular languages are closed under intersection, the intersection of L2 with the language of the regular expression 0 star 1 star would also be regular. Now the language of 0 star 1 star is all strings with any number of zeros followed by any number of ones. But what is the intersection of L2 with this language? It is L1 because L2 forces the number of zeros and ones to be equal, while the language of 0 star 1 star forces all the zeros to precede all the ones. Set difference is another operation under which regular languages are closed. The difference of languages L and M, written L minus M, is the set of strings in L that are not in M. For the proof of closure under difference, start with DFAs A and B for languages L and M respectively. Construct C the product automaton for A and B. Make the final states of C be the pairs where the state from A is final and the state from B is not. Then C accepts an input string W if and only if A accepts W but B does not. That is, W is in the difference of their languages. Here's our favorite product automaton again. This time, BD is the only final state. Because B is the only final state of the orange automaton, and D is the only non-final state of the purple automaton. Notice that the final state BD is not reachable from the start state, so this version of the product automaton accepts the empty language. That's exactly as it should be because the first automaton, the orange one, accepts a subset of what the second automaton, the purple one, accepts. That is, the first automaton accepts all strings that end in an odd number of ones, while the second accepts all strings that end in at least one one, plus the empty string. The complement of a language is defined with respect to some alphabet sigma. Sigma has to include all the symbols from the alphabet of the language L, but may include other symbols that don't appear in L. Then the complement of L is all strings in sigma star that are not in L. Since sigma star is surely a regular language, and we know that regular languages are closed under difference, we immediately know that the complement of any regular language is also regular. Now we shall look at the operation of reversal. Recall one of our earliest examples of a regular language was the language of binary strings that, when interpreted as integers in binary, were divisible by 23. We commented then that the language of such strings that, when reversed, were divisible by 23 was also a regular language. We also said that constructing a DFA for that language is tricky. So here's the tricky construction, which really isn't so tricky now that we have mechanisms like regular expressions to work with. First, the notation we use for reversal is superscript R. That is, L super R means the reversal of language L. This language consists of the reversals of all the strings in L. Here's a simple example. L has three strings, 0, 0, 1, and 1, 0. Then L reversed is the reversal of each of these strings. 0 reversed is still 0, while 0, 1 reversed is 1, 0, and 1, 0, 0 reversed is 0, 0, 1. So L reversed consists of 0, 1, 0, and 0, 0, 1. To begin the proof that regular languages are closed under reversal, we start with a regular expression for a regular language L. We'll show by an induction on the number of operators in the regular expression that there is a regular expression for the reverse of L. The basis is expressions that are either single symbols, the empty string, or the empty set. These are the only expressions with zero occurrences of operators. In all these cases, the expression doesn't change. That is, the reversal of a string of length 1 is the same string. The reversal of the empty string is still the empty string, and if you reverse all strings in the empty set, the set is still empty. The induction consists of the three operators for regular expressions. For union, it is easy. You just reverse the expressions for the two parts of the union. Concatenation is a little trickier. To reverse a string WX, where W comes from F, say, and X comes from G, you need to reverse W and reverse X, but then you need to flip the order of the reverse strings. That is, X reversed comes before W reversed. For example, if W is 0, 1, 1, it's W, and X is 0, 1, then the W reversed is 1, 1, 0, and x reversed is 1, 0, but the x has to come first, so the reverse of 0, 1, 1, 0, 1 is in fact 1, 0, 1, 1, 0. And for the star, we reverse the expression f that is starred. That's this guy here. So it now produces the reverses of all the strings that f produces. We then star the reversed expression to get concatenations of any number of the reverse strings in any order. Let's reverse this regular expression. Its language is all strings of zeros and ones such that the first bit never again appears. That is, the strings are either a 0 followed by any number of ones, that's this part, or a 1 followed by any number of zeros, that's that. The outermost operator of this expression is the plus, and the way we reverse a sum of two expressions is to reverse each expression separately. That is, the reverse of this whole expression is the reverse of the two parts separately. Now let's look at one of the expressions 0, 1 star. We have to, let's look at this. We have to reverse it. So the way we reverse a concatenation is to reverse each of the component expressions and put them in reverse order. So 0, 1 star, its reverse is 1 star reversed followed by 0 reversed. The other expression, 1, 0 star, which must be reversed, is handled the same way. It's 0 star, and we have to reverse that, followed by 1, which we must reverse. Okay. The basis rule tells us the reversal of 0 is 0, and the reversal of 1 is 1. That is, the reversal of this 0 is just that 0, and the reversal of 1, again, is just that 1. Also, the reversal of 1 star is the star of the reversal of 1. That's that. And similarly, the reversal of 0 star is the star of 0 reversed. Finally, the reversal of 1 again, that's this, is just 1. So we get 1 star 0. And the reversal of 0 again is just 0, and we get that. Now we have no reversals left, and we are done. The resulting expression is what you would expect. Its language is the binary strings where the last symbol does not appear elsewhere. Homomorphisms are transformations on symbols that replace each symbol by a string, which may be empty, another symbol, or a long string. When a given homomorphism is applied to all the strings of a regular language, the result is a regular language, as we shall see. Here's an example of a homomorphism, one that we shall use repeatedly in the discussion. This homomorphism H replaces every 0 by the string AB and replaces every 1 by the empty string. We apply any homomorphism to a string by applying the homomorphism to every symbol of the string in order and concatenating the results. For example, if we apply our homomorphism H to the string 0, 1, 0, 1, 0, each of the zeros gets replaced by AB, and the ones effectively disappear because they are replaced by the empty string. That is, this 0 becomes that AB, this 0 becomes that AB, that 0 becomes that AB, and the ones are replaced by epsilons that sort of go in the middle there, but you don't see them, of course, because they're empty. Thus, H of 0, 1, 0, 1, 0 is AB, AB, AB. We claim that if you take a regular language L and apply a homomorphism H, then the result is also a regular language. Note that the result of applying H to the language L is the set of strings you get by applying H to all strings in L. I'm not going to give you a formal proof, but the big idea is that you start with a regular expression for L, and you apply H to every symbol in that regular expression. The result will be a regular expression for L. Here's a simple example. H is the homomorphism we have been using as an example right along, and L is also a language whose regular expression E we saw before in connection with reversal. We compute an expression for h of L by replacing each occurrence of 0 in E by AB and each occurrence of 1 by the empty string. The resulting expression is this one. Okay. That is, this 0 got replaced by AB, this 1 got replaced by the empty string, that 1 got replaced by the empty string, and this 0 got replaced by AB. By the way, here is a good example where you have to introduce parentheses, since 0 star needs no parentheses, but AB star, that is, if I wrote just this, would be wrongly interpreted as an A followed by any number of B's. Rather, what we mean is any number of unit ABs. We can simplify this expression considerably. First, epsilon star is any number of empty strings, so we can replace AB epsilon star, that's this, by just AB epsilon. Remember that the empty string is the identity under concatenation. So we can remove the epsilons to give us just AB plus AB star. That is, these guys go away, leaving us just that. Okay. But the language of AB is just one occurrence of AB, while the language of AB star is any number of occurrences of AB, including exactly one occurrence. Thus, we can just drop the term AB here, and we are left with just AB star. That's the simplified expression. We can also define the inverse homomorphism of a language or a string. We denote inverse homomorphisms by a superscript -1. That's this notation here. The result of applying the inverse of a homomorphism H to a language L is the set of strings W, such that when you apply H in the forward direction to W, you get a string in L. So here is the language L. These are all the strings in the language L. Okay. And H will be represented by downward motion. So any string that goes anywhere in L, when you apply H, these are all in H inverse of L. And any string that misses L when you apply H, that's not in H inverse of L. Here's an example. Let H be the homomorphism of our running example. L is the language with two strings, ABAB and BABA. Okay. That's that right there. Then H inverse of L is the language of strings that have two zeros and any number of ones interspersed. Here's a regular expression for this language. To see why, let's look at the two strings in L. Okay, ABAB and BABA. A string like 11011101 maps to ABAB. The ones disappear as they go to empty string, and the first zero goes to that AB, the second zero goes to that AB. But nothing can go to BABA because a zero say, has to cover that AB in the middle. That's the only way you can map a zero. Now you've got to be able to map something to the B, but the only way you can do that is if you have a zero, but that would then map to AB. And similarly, this A, there's no way to map to that A without mapping to another B which doesn't exist. While for forward homomorphism, the regular expression representation was dandy. To show that the inverse homomorphism of a regular language is regular is best done with DFAs. Okay. Start with a DFA A for L and construct a DFA B for H inverse of L. B has almost everything the same as A, the same states, the same start state, the same final state. But the input alphabet for B is the appropriate input alphabet, that is, the set of symbols to which the homomorphism H applies. We then fix up the transition function for B to reflect both the new set of input symbols and the effect on those symbols of the homomorphism. Suppose B is in state Q and the input symbol is A. We apply H to A, and we see where the automaton capital A would go on that sequence of inputs H of A. That is, delta B of Q and A is delta A, that is the transition function for the automaton A, starting at state Q, but reading sequence H of A. Note that H of A could be the empty string or some long string of symbols. So this is really the extended delta, but that's okay. We know what that is. Here's an example automaton, and we'll use the same homomorphism we've been playing with all along. Since H of 1 is the empty string, each state of the automaton for the inverse homomorphism will transition to itself on 1. That's what these transitions, for example, are suggesting. For transitions on 0, we need to figure out where the original automaton goes on AB. For example, starting in state A and following the path labeled AB, you wind up in state C. That explains why the transition from A on 0 goes to C. Similarly, starting at B and following the path labeled AB, it's that, you also get to C. And the same thing is true if you start from C, you get A and then B. We're not going to do the complete proof that regular languages are closed under inverse homomorphism. The heart of the proof is an induction on the length of W that says that W takes automaton B from the start state to state P, if and only if the string H of W takes automaton A from the start state to the same state P. That's this equation. Now B accepts W and A accepts H of W if and only if P is a final state. That is, W is in the language of B if and only if H of W is in the language of A, which is the same thing as saying B accepts the H inverse of the language of A.